Hello guys, welcome to another video on tolerance stackup analysis. In this video, we'll be exploring the differences between worst case tolerance stackup analysis method and the root sum squared tolerance analysis method. So by analysis method, tolerance stackup analysis can be divided into two types. One is the worst case, when we consider the variations of specification to be at their extreme in the worst case, and statistical method when we consider the probability of variation. So in that, there are two types: root sum squared method, and then there is the Monte Carlo simulations method, which is a more advanced method, which is generally used in software, in tolerance stackup analysis software, to simulate the variations in various specifications of parts in mechanical design. So here we will understand the two worst case versus root sum squared and see the differences. First, let us understand what do we mean by worst case analysis. So when we say worst case analysis, and let's say, for example, if you are having a step shaft as shown, which is having a specification as shown, 17 plus or minus 0.2 is the length. Now, when we say worst case, we mean that we are considering uniform distribution of probability. That is, when a part is being manufactured in the manufacturing line, the probability of that part being at its least value, that is in this case it's 16.8, the probability of the part being at 16.8 is the same as the probability of the part being at 17.2. So basically we are saying that the probability that the manufacturer will manufacture this part at 17.2 is the same as that if it is manufactured at 17, that is the nominal, and that is the same as if it's manufactured at 16.8. This is called as the uniform probability distribution, in which we are saying that the probability of manufacture at extremes is the same as that as it is nominal or at the mean. This is the underlying assumption in worst case analysis. So when we do a worst case analysis stack up, as in this case, so let's say we are having a step shaft, the complete length is given, and the length of this step is given, and the length of this step is given, which is 11 plus or minus 0.2, 2.5 plus or minus 0.1, and 17 plus or minus 0.2. These are the tolerances which are associated with these length dimensions. Then what would be the specification for A to B? So we can calculate that using the loop diagram. Starting from A, we start the loop diagram going towards the left. That is the first specification, which is 2.5 plus or minus 0.1. Then going towards the right, that is the second specification, which is 17 plus or minus 0.2. And then the third specification is this one, which is 11 plus or minus 0.2. We create the table. So the first one is 2.5 plus or minus 1. So dimension is 2.5. The direction is towards the left, considering towards the left to be minus and towards the right to be plus. So this is minus. Then the second dimension is plus 17. Third dimension is minus 11 because it is again going towards the left. And the tolerance is, we add the tolerances. So 0.1, 0.2 and 0.2 we add, we get 0.5, and then we basically calculate this by subtracting the value from 17, we get 3.5. So the nominal specification for A to B is 3.5, and the variation it can have is plus or minus 0.5, considering the stack up of 1, 2 and 3. So the specification for gap AB will be 3.5 plus or minus 0.5. And if you are considering uniform distribution, the probability that it can be at its highest, that is 4 mm, is the same as if it is at its lowest, that is 3 mm. So worst case highest is 4 mm, worst case lowest is 3 mm. Now that brings us to root sum squared method and the underlying principle of normal probability distribution. Normal distribution, in which we are saying that the probability of the specification, which is shown over here 17 plus or minus 0.2, the probability of it being at its extremes, which is 16.8 and 17.2, will be very less as compared to the probability of being manufactured at the nominal, which is the highest. So basically the normal distribution, which is otherwise called as the bell curve, we say that manufacturing processes follow this normal distribution, which means that when we manufacture a part from a manufacturing process, let's say for example a lathe machine, a machine tool, then the probability that the part will be at 17.2 is very less as compared to the part being at 17, which is the nominal. And also the part being at 16.8, the probability of that is very, very less as compared to it being at its nominal, at its mean. So that is the main assumption over here, underlying assumption for root sum squared method, that the dimensions follow a normal distribution, bell curve. And most parts, majority of the parts are manufactured close to the nominal specification, which is the mean. And important assumption is that it is statistically unlikely that all specs will be at their extreme limits simultaneously. So as in the case of the earlier Stackup, which we had seen 1, 2, 3, in that case, the probability of all of the three specifications being at their extremes simultaneously is very, very low. Statistically, it's very, very low if we are considering the variations to follow the normal distribution. And it is seen that most of the processes, manufacturing processes, follow the normal distribution, which are the most common ones, basically follow the normal distribution. Hence, using a worst case analysis, worst case tolerance Stackup analysis in that case would be designing too conservatively. Instead of that, we can use a root sum squared method. So that is basically the rationale behind using root sum squared method as opposed to worst case analysis. To understand root sum squared method, we need to understand the terms of standard deviation and variance. So let us understand with this example. Let's say, for example, one type of manufacturing process is manufacturing this part with this dimension and specification, 17 plus or minus 0.2 as shown. This is the upper limit and this is the lower limit. Mu indicates the mean. This center line is the mean. And if the probability distribution, let's say if 1,000 parts are manufactured and the 1,000 parts are measured in terms of this dimension, and it is found that the probability distribution is something like this. That is, the probability of finding a part which is having a value of 17, that is nominal mean, is highest, and it drops down drastically as we move towards the lower limit and upper limit. This process 1 will have less spread. So the spread is small. Whereas in process 2, if we consider the process 2, and if the graph turns out to be something like this, the spread is much wider as compared to process 1. So in that case, the probability of finding paths which are away from the mean is much higher in the case of process 2 as compared to process 1, which means that the standard deviation, which is a measure of how spread out data points are with respect to the mean, is higher in process 2 as compared to process 1. So basically, standard deviation as a concept is a measure of how much spread out the data points, the probability of finding a path away from the mean is. If the probability of finding a path away from the mean is larger and larger, then the standard deviation becomes larger, as shown over here. So these regions, the green regions, the blue regions, as they become bigger and bigger, the standard deviation will be larger. But if they become narrower, then the standard deviation becomes lesser. Ideally, we would want the standard deviation to be as low as possible, which is basically meaning that we want the manufactured parts to be as close to mean as possible. We can say that process 1 is better than process 2 because most of the parts being manufactured are near to the mean. But practically, it is not always the case. Standard deviation varies from process to process, and that is to be factored in. Variance is another important term which is used to define the spread of data. Variance is the average squared deviation from the mean, which is statistically calculated, and variance is generally the square of the standard deviation. So whatever the standard deviation of a process, the square of that standard deviation is equal to the variance, and variance can be calculated by calculating the deviation, the squared deviation from the mean, and averaging out that squared deviation from the mean if we are having a data set. So let's say if we are having 10 data sets and we are having a mean of that data, then if we calculate the deviation and then square that deviation and find the average of that squared deviation, that would be the variance of the data, and that is square of standard deviation. So variance and standard deviation are basically used to measure the spread of data points with respect to the mean for a process. Now let's have a look at the differences between 1 sigma process and 3 sigma process, which again extends to 6 sigma. 6 sigma being a very popular concept in industrial processes, which is basically a concept derived from the basics of normal distribution. So what do we mean by 1 sigma and 3 sigma? So let's say if you're having a process which manufactures parts with respect to a normal probability distribution as shown. Now, if the limits, the upper specification limits and lower specification limits are located from the mean, which is 0 over here, at 1 sigma, that is plus sigma, and minus sigma, that is 1 sigma on either side, then this process is called as the 1 sigma process. As you can see, the limits are over here. These two lines indicate the limits, upper and lower specification limits. If that is the case, then there will be parts which will be manufactured which are considered to be defective, which will fall outside these limits. Whereas if you are having a manufacturing process in which the limits, the upper and specification limits are spaced at plus 3 sigma and minus 3 sigma from the mean as shown, then the number of defects will be much lesser. So a process which is able to manufacture with plus or minus 3 sigma is a superior process as compared to a process which is able to manufacture at plus or minus 1 sigma, which is shown over here in the table. So let's say if you are having a process which is manufactured at plus or minus 1 sigma and the upper and lower specification limit is as shown, then the defects which are showing up in, let's say, 1,000 parts will be much higher in a 1 sigma process, but the defects which are showing up in a 3 sigma process will be much lower, which is shown over here, very small area. So that is shown in percentage over here, 31.73% defect rate in 1 sigma, and 3 sigma 0.27% defect rate. So defects per million opportunities, that is million manufactured parts, is 317,310 for 1 sigma process and 2,700 for 3 sigma process. So there is no zero defect in 3 sigma process, but the number of defects is drastically reduced. So in other words, we can say that if we are having two processes, one process is more capable than the other in manufacturing parts which are acceptable and less defective. So here in this case, since the upper and lower limit are over here, the probability of this process to manufacture parts which are defective above the upper or lower limit is much higher as compared to the probability of this process to manufacture parts which are above or lower the upper or lower limit. So in this case, in the 1 sigma process, there is more probability of defects coming up in the, let's say, 1,000,000 parts being manufactured, whereas over here the probability of defects coming up is much lesser. So that's the difference. It is important to differentiate between the terms tolerance and standard deviation. Tolerance represents the absolute range, which is nothing but the range between upper limit and lower limit, whereas standard deviation is related to the process. Standard deviation represents the statistical probability of variation, which is nothing but the spread of the process. So tolerance can be different for different types of specification which are manufactured for based on a process, but the standard deviation for the process remains the same. And the relation between tolerance and the standard deviation is given by sigma is equal to T by K, where T is the unilateral tolerance as considered in worst case, which over here is nothing but 0.2, and K is the statistical factor. And this statistical factor is 3 for plus or minus 3 sigma process, and it is 1 for plus or minus 1 sigma process. So if you are considering a process to be plus or minus 3 sigma, then this K is equal to 3. And then we can calculate the tolerance based on the standard deviation, or based on the tolerance you can calculate the standard deviation, either way around. General standard industry practice is to assume that the manufacturing process is plus or minus 3 sigma process, especially when the process is being used for mass production. For generic processes like CNC machining, these processes are considered to be plus or minus 3 sigma processes. It's an assumption. If the quality of the process is lower, then we need to consider a lower value over here. Generally, we consider for standard industry processes, plus or minus 3 sigma process for a manufacturing process is considered for calculations. So in that case, sigma is equal to T by 3. So over here, if I want to calculate this sigma, then it will be sigma is equal to 0.2 by 3, which is nothing but 0.066, which will be a standard deviation of a process which is used to manufacture a part which is having this specification. Variance is sigma squared, that is square of this value, which is 0.004356, that is variance. And the main assumption implies that the manufacturing process which is used to manufacture a part with the specification as shown is 3 sigma capable process, and that 99.73% of all the parts which it produces will fall within the specified tolerance limits, and it will be normally distributed. That's the main assumption over here. Then if we had to redo the tolerance stack-up analysis with whatever we have learned considering the standard deviation by converting the tolerance ranges to their respective standard deviations and finding out the standard deviation for the gap AB, then the process would be something like this. First of all, we calculate the standard deviations for these specifications, these tolerances, plus or minus 0.1, plus or minus 0.2, plus or minus 0.2 over here. These would be sigma 1, sigma 2 and sigma 3. Then we find out the squares of these and add them, which will be the variance. So sigma squared is equal to sigma AB the whole squared is equal to sigma 1 squared plus sigma 2 squared plus sigma 3 squared. And then from that, by taking the root, we can find out the standard deviation of AB, which is root of sigma 1 squared plus sigma 2 squared plus sigma 3 squared. So this formula basically gives the name of root sum squared. As you can see, it is the root of the sum of squares, which is root of sigma 1 squared plus sigma 2 squared plus sigma 3 squared, which is standard deviation of the gap AB. So if we calculate it in the table, we have the dimensions, we have the tolerances T, 0.1, 0.2, 0.2, and from the worst case analysis, we had 0.5. Now if we calculate the standard deviations for 0.1, 0.2 and 0.2, we get these values, and then if we square them, we get these values for variance, and then we sum the squares and then take the root. If we sum the squares and take the root, we get the standard deviation for specification AB, and that standard deviation comes out to be plus or minus 0.1. So standard deviation is plus or minus 0.1 mm from this calculation, considering sigma is equal to T by 3. This is an important assumption. We are assuming that the process which is used to manufacture all of these specifications is a plus or minus 3 sigma process. So the result which we get is in the form of the standard deviation of the gap AB. And if we know the standard deviation, we can calculate the corresponding tolerance range which we should have for AB by using this formula again. So it will be nothing but 0.1 into 3, which is plus or minus 0.3 mm. So the corresponding tolerance, RSS tolerance, that is not the normal tolerance, it is the RSS tolerance, is 0.3, which is lesser than 0.5. That calculation is shown over here, which is a simplified version of the tolerance calculation, which is avoiding the standard deviation terminology, which is a simplified version. Important to know that RSS is derived from the concept of normal distribution and standard deviation, but a simplification would be to use a term called as RSS tolerance, which is TRSS as shown over here, which is nothing but plus or minus root of T1 squared plus T2 squared plus T3 squared, root sum squared method. So when we do this, we get the TRSS, which is plus or minus 0.3 mm. which is not as strict or not as worst case as 0.5 mm. So why is RSS useful? First of all, you can see that RSS is a liberal form of the tolerance stackup because it yields a value which is lesser. This is a more worst case value, plus or minus 0.5. But if you are having a controlled process, a controlled manufacturing processes which are in place, and we know that the manufacturing processes follow a normal distribution and they are plus or minus 3 sigma processes or whatever that value is in terms of sigma, in terms of standard deviation, then we can calculate using this formula, and that would give us a realistic tolerance, RSS tolerance, whereas this worst case is considering all of the variations are at the worst possible case, which is not possible, practically possible. So where do we use RSS tolerance? RSS tolerance has to be used in cases where the processes are controlled, but in cases where there is critical interference which can occur or critical issues which can occur in the assembly, in that case, a conservative approach like worst case analysis can be used. But in other cases where manufacturing processes are controlled and are known or measured, in that case, RSS tolerance generally suffices.